Welcome to Deep Dive with Emily and Phil. Today, we're going to take a deep dive into machine learning and tackle a concept called regularization.
Regularization.
That sounds kind of intimidating, right?
Yeah, it might sound complex, but at its heart, regularization is all about making sure our machine learning models don't get carried away.
Okay.
You know, like that student who crams for a test and aces it, but then forgets everything the next day.
Right.
We want our models to truly understand the patterns in the data, not just memorize them.
So it's like teaching our models to see the forest, not just the trees.
Exactly.
I like that.
Yeah.
But how do we actually do that?
Okay.
My notes mention something called the bias-variance trade-off. What's that all about?
That's the key. Remember, we want our models to be both accurate and flexible.
Okay.
Bias is all about accuracy, how far off our model's predictions are on average. Variance, on the other hand, measures how much those predictions jump around.
Okay, so high bias means our model is consistently wrong, and high variance means it's unpredictable.
Exactly. And when we create a super complex model trying to fit our data perfectly, we risk overfitting.
Okay.
It's like the model is so focused on the individual data points that it misses the bigger picture, leading to high variance.
Got it.
Regularization helps us find that sweet spot between accuracy and flexibility.
So regularization is like adding a bit of guidance to our models, preventing them from getting lost in the weeds of the data.
Precisely. It's like setting some healthy boundaries. And how do we do that?
Yeah, how do
We introduce constraints.
Okay.
We tell our models, hey, you need to minimize prediction errors, but you also need to keep your weights in check.
Weights. What are those in this context?
Think of weights as the importance our model assigns to different features. Large weights can mean the model is relying too heavily on certain features, potentially leading to overfitting.
Got it.
Yeah.
So by keeping the weight small, we're encouraging the model to find a more balanced explanation, right?
Yeah.
But how do we actually enforce these constraints?
This is where the fun begins.
Okay. We have a few tools at our disposal. LASSO ridge regression and elastic net.
Yeah.
Each uses a slightly different type of constraint to nudge those weights in the right direction.
Okay, I'm intrigued. Let's break them down one by one.
Yeah.
What's so special about LASSO?
LASSO is like that strict teacher who gives you extra homework if your model uses too many features. Technically speaking, it adds an L1 norm penalty to the regression objective,
Okay.
essentially penalizing the model for having large weights.
So it's like LASSO is encouraging the model to be concise and focus on the most important features.
Exactly. And then we have ridge regression.
Is that the more lenient teacher?
You could say that. Ridge regression adds an L2 norm penalty to the regression objective.
Okay.
It still encourages smaller weights, but it's a bit more forgiving than LASSO.
Interesting. And what about elastic net? Where does that fit in?
Elastic net is like a blend of both teaching styles. It adds both L1 and L2 norm penalties to the regression objective,
Oh.
giving us more flexibility in controlling the model's behavior. So elastic net is the balanced approach combining the best of both worlds.
You got it. It's all about finding the right tool for the job.
This is fascinating. We're essentially shaping how our models learn by adding these constraints.
Yes.
But how do those constraints actually play out when the model is trying to find the best solution? I remember from my notes something about gradient descent.
Ah, yes.
Yeah.
Gradient descent is the algorithm that helps our model navigate the landscape of possible solutions to find the best one. Imagine it like a hiker trying to find the lowest point in a valley.
Okay, I can picture that.
Yeah.
So how do our constraints affect the hiker's journey?
Well, those constraints change the shape of the valley.
Okay.
They create boundaries guiding the hiker towards solutions with smaller weights, even if those solutions aren't the absolute lowest point in the original valley.
So we're subtly influencing the model's choices, pushing it towards a more balanced and generalizable solution.
Exactly. It's all about finding that sweet spot between fitting the data well and keeping those weights under control.
Okay, that makes sense. But I have to ask, can't we accidentally push the model too far and make it too simple?
That's a great question, and it leads us to our next fascinating concept. Lambda.
Ooh.
Yeah. Lambda is like a control knob for our constraints.
Okay.
It allows us to fine-tune how much emphasis we place on keeping those weights small.
So it's like setting the difficulty level for our model.
Yeah.
A high lambda means be super strict with those weights, and a low lambda gives the model a bit more freedom.
That's a fantastic way to put it.
Okay.
And this lambda value is what we call a hyperparameter. It's something we need to decide before we even start training the model.
So it's like giving our model some helpful hints before it sets off on its learning journey.
Exactly. And finding the right lambda value is a bit of an art.
Okay.
We want to find a balance where the model is constrained enough to avoid overfitting, but not so constrained that it undersits the data.
Underfitting. That's when our model is too simple and can't capture the nuances of the data, right?
Yes.
Like trying to fit a straight line to a data set that clearly has curves.
Precisely. And just like with Goldilocks and the Three Bears, we're looking for that just right lambda value.
Okay. I'm starting to see how important lambda is. But how do we actually find that perfect value? It sounds like a lot of trial and error.
There are more systematic approaches than just randomly guessing. One common technique is cross-validation.
Okay.
We divide our data into multiple folds, train our model on some of those folds using different lambda values, and then test it on the remaining folds to see how well it performs.
So it's like giving our model a series of practice tests with different levels of difficulty to see which lambda value helps it learn best.
That's a great analogy. By comparing the performance across different lambda values, we can identify the one that leads to the most robust and generalizable model.
This is making a lot more sense now. We're not just throwing our model into the deep end. We're carefully guiding it with constraints and fine-tuning its learning process with lambda.
And speaking of guidance, remember how we talked about those model weights telling a story? Yeah.
Let's say we're using linear regression to predict something like, the percentage of someone getting cancer based on the levels of different proteins in their blood.
Okay, so each protein level is a feature, and our model is trying to find the relationship between those features and the likelihood of cancer.
Exactly. Now imagine we've trained our model and we get these weights. 76 for protein 1, 6 for protein 2, and 0.00001 for protein 3. What does that tell you?
Well, it seems like protein 1 is a much stronger predictor than protein 3. That weight for protein 3 is practically 0.
Precisely. The weights reveal the importance of each feature in the model's prediction. In this case, protein 1 is screaming, hey, pay attention to me, while protein 3 is barely whispering.
So the weights don't just tell us what the model predicts, but also why it's making those predictions.
Exactly. They provide a glimpse into the model's reasoning, which is incredibly valuable for understanding how it works.
Yeah.
Remember Professor Wu's lecture where he compared linear regression with L2 norm ridge regression and L1 norm?
LASSO.
Yeah, he showed how each method performed in terms of accuracy and weight values. The results were really interesting. Linear regression without any regularization was the most accurate, but the weights were all over the place.
It was like the model was trying to juggle too many things at once, leading to a bit of chaos.
Then with L2 regularization, the accuracy was almost as good as plain linear regression, but the weights were noticeably smaller.
L2 gently nudged those weights towards 0, bringing a bit more order to the model's thinking.
And that's where L1 regularization really stood out. The accuracy took a slight hit, but many of the weights were pushed all the way to 0.
It was like L1 helped the model prioritize and focus on the most important features, even if it meant sacrificing a tiny bit of accuracy.
So it's a trade-off we need to consider. Do we want the most accurate model possible? Or do we want a model that's easier to interpret and understand?
That's the million-dollar question.
Right?
Sometimes that interpretability is crucial. If we can pinpoint the key drivers of a prediction, it gives us more confidence in the model and helps us make better decisions. But what's really cool is that we don't always have to choose just one. Remember, ElasticNet.
Oh yeah, the one that combines L1 and L2 penalties. Does that mean we can fine-tune how much we prioritize accuracy versus interpretability?
You got it. ElasticNet gives us that flexibility. It's like having a dimmer switch for each type of penalty, allowing us to find the perfect balance for our specific needs.
So we've got all these tools, LASSO, Ridge Regression, ElasticNet, and this Lambda thing to help us build better models. But it also sounds like there are a lot of decisions to make. How do we know which approach is best for a particular problem?
That's where experience and a bit of intuition come in. There's no one-size-fits-all answer.
Sure.
It often involves experimenting with different approaches, analyzing the results, and refining our strategies. It's a bit like being a detective searching for clues to build the most robust and insightful model possible.
This has been incredibly enlightening.
Wow.
I feel like I'm finally starting to grasp the power and nuance of regularization.
It's a fascinating topic, and there's always more to explore. But for now, I think we've covered the essentials.
This deep dive has definitely opened my eyes to the importance of thinking carefully about how our models learn. It's not just about throwing data at an algorithm. It's about shaping that learning process to create models that are both powerful and insightful.
Well said. And with that, I think it's time to wrap up this deep dive.
Agreed. Regularization, you've officially been demystified.
It's been really fun exploring all this with you.
Yeah, I agree. It's amazing how a concept that seems so simple can have such a huge impact on how our models learn. It's like we just unlocked a secret level in machine learning.
And who knows what other exciting discoveries are out there as we keep digging deeper into machine learning.
Right. That's what I love about this field. There's always something new to learn and explore. It's like it never ends.
Well said. I think it's about time we wrap up our deep dive into regularization.
Yeah, I think we covered a lot today.
We did.
And hopefully our listeners have a new appreciation for how important regularization is in shaping the future of machine learning.
Absolutely. Until next time, may your models be well regularized and your insights be profound.
And to all our listeners, keep on learning, keep on exploring, and keep on diving deep.